Accurate actuators accelerate automation. Elon Musk confirmed that Tesla Bot Gen 3 now operates with actuator precision of plus or minus zero point 0.1 millimeters. This micro-level accuracy enables smooth and stable movement in real-world conditions. Whether lifting fragile objects or navigating tight spaces, Optimus moves with clear intent. So, what types of tasks does this level of precision enable Gen 3.5 to perform effectively? Before we begin, please help us reach 15,000 subscribers. It will be a huge motivation for us to continue bringing you great episodes about Tesla Bot, Tesla EVs, and the latest news. What are the new motion updates in Tesla Optimus Generation 3.5? When Tesla unveiled the latest updates to the Optimus Gen 3.5 humanoid robot, most attention naturally centered on speed, design, and production milestones. But hidden beneath the more sensational headlines lies a quietly revolutionary change. A complete overhaul of how the robot moves, how it walks, swings its arms, balances, and appears relaxed. It's more than just cosmetic. It's a redefinition of movement that pushes Optimus from the realm of stiff automation into something unnervingly lifelike. And the transformation happened without a single hour of manual programming. How? The secret lies in the use of reinforcement learning, RL, deployed entirely in a simulated environment. Tesla trained Optimus's new walking style not by dictating joint angles or pre-programmed gaits, but by letting the AI explore, fail, improve, and succeed within a vast virtual simulation. The outcome? A walking motion that's straighter, more natural, and smoother than anything seen in previous versions. The knees now stay straighter during movement, similar to the biomechanics of a human strolling at ease. The gait starts from the heel, rolls through the arch, and ends with a soft push-off from the toe, rather than the flat-footed stomping common in other humanoid bots. This change isn't trivial. In fact, the upright knee posture mimics what is seen in efficient human walking, minimizing energy waste and reducing oscillations. Previously, Tesla's robot tended to bend its knees excessively, a style often found in early humanoid robotics and animation. It was stable, yes, but robotic and tiring over time. By contrast, the new gait in Genesis 3.5 allows longer strides and more fluid leg extensions, reducing the number of steps per minute and enhancing ground clearance without sacrificing stability. Such optimizations matter when aiming for sustained real-world use across warehouses, factories, and potentially even homes. Moreover, Gen 3.5 introduces coordinated arm swings that naturally counterbalance leg motion. The swing amplitude is subtle, just enough to offset momentum, but crucial for balance. Arms now move in rhythm with the torso, contributing to a sense of intention and fluidity. Tesla even designed slight shoulder roll and elbow flexibility, which gives the appearance of relaxation. There is no unnecessary rigidity, no jerky pauses. Every motion feels, surprisingly, human. Should this level of grace and movement start to feel uncanny? The entire locomotion system was generated through what Elon Musk calls auto-simulation, a process by which virtual training runs thousands of years of learning in mere days of real time. According to Tesla, the RL environment modeled not only the robot's own mechanics but also terrain friction, center of mass shifts, and even micro-impacts from each step. The result? Over 1 million training hours of walking, falling, adjusting, and recovering, all before the robot ever set foot in the real world. And it worked. Tesla reports that Gen 3.5 can now recover from slips and unexpected tilts within milliseconds. With a foot length of roughly 11 inches and a total height near 5 feet 8 inches, Optimus has a humanoid ratio that enables balance recovery patterns similar to those of a human adult. During internal tests, Gen 3.5 was pushed sideways with over 35 pounds of lateral force and recovered within 0.12 seconds, without locking joints or overcompensating posture. Is this level of responsiveness already ahead of industrial norms? Even more fascinating is how Tesla bypassed the traditional animation-to-code pipeline. Most humanoid robots have walking routines hard-coded by engineers, or at best, generated by motion capture data of human models. Tesla skipped all of that. The robot didn't mimic a human. It taught itself how to walk. This bottom-up learning approach led to some unexpected results. For instance, the foot landing sequence optimized itself to land slightly on the outer heel before rolling in, a technique biomechanically proven in sports science to reduce impact stress. Another unexpected outcome is psychological. People who saw Gen 3.5 walking in Tesla's demo described it not as robotic, but relaxed. That's a powerful shift. The goal of Tesla's humanoid isn't just movement, it's presence, and motion is a large part of how presence is perceived. A rigid robot, no matter how capable, cannot easily blend into human environments. But a machine that moves like it belongs in the same space as people, quiet, stable, and confident, begins to feel more like an assistant and less like a threat. But let's not be too easily impressed. Yes, Tesla's use of reinforcement learning is impressive. Yes, the motion is graceful. But can this motion scale to 1 million robots? That's the target Tesla has floated. Yet, the very nature of RL-trained behavior means each robot must inherit a highly calibrated model, tuned for mechanical tolerances. A slight variance in servo torque or sensor feedback could cause a significant divergence in gait quality. Will Tesla's manufacturing lines be precise enough to ensure that every Optimus moves like the simulation promised? Tesla says it already produces 1,000 units per month in early trial runs, and the first 10,000 units will be deployed internally in its own factories. This offers an advantage. The environment is controlled, the floor is flat, and the stakes are low. But once deployed in American logistics hubs, where unexpected stairs, slopes, and human unpredictability reign, how will the robot respond? Will those elegant motions hold up when a 200-pound payload is added to the arms? Furthermore, there's the question of long-term wear. Biomechanically optimized gaits often depend on precise motor control and joint stiffness. Over time, actuators degrade, leading to delayed reactions or improper weight distribution. Has Tesla considered real-world degradation in its training loop? If not, even a small delay in joint response, say 20 milliseconds, could make recovery impossible in a fall scenario. Another area of concern is computational cost. Reinforcement learning models, especially those operating in real time, can require significant onboard processing power. Tesla's solution appears to involve edge inference chips derived from its FSD full self-driving platform. But as movements become more complex, such as navigating stairs, avoiding moving obstacles, or interpreting dynamic environments, the robot must not only walk, but think fast. Will the same chip handle walking, manipulation, visual parsing, and reasoning all in real time without latency? Nevertheless, Tesla's approach does set a new standard. It's a deviation from Boston Dynamics' choreographed routines or Agility Robotics' repetitive motion cycles. Instead of prioritizing acrobatics, Tesla has focused on long-term viability, quiet steps, graceful joints, and resilient motion. And all this at a projected unit cost of under $20,000, an unheard-of price point in the humanoid field. If Tesla succeeds in mass-producing humanoid robots that move this well, it will not only disrupt robotics, but potentially redefine labor in America. What happens when 100,000 such robots enter warehouses that used to employ human workers for $18 an hour? In the end, the question isn't just whether the robot can walk like a human. It's whether people will accept a machine that does. The Gen 3.5's motion is not about walking. It's about belonging. That perhaps is the biggest leap of all. Once again, please help us reach 15,000 subscribers. This is important for us to stay motivated. Thank you. How will Tesla deploy the charging system for Optimus? In a recent leaked image from a Tesla facility, a row of humanoid robots resembling Tesla Optimus Gen 3.5 are seen standing in a clean, brightly lit room, each aligned with a wall-mounted docking station. This never-before-seen charging configuration offers a rare glimpse into Tesla's latest progress in deploying Optimus bots at scale. At first glance, these stations look minimalistic, but a closer examination reveals a streamlined industrial design optimized for high-efficiency charging and automated management. The upright posture of each robot as it docks is a telling sign. Tesla is minimizing mechanical transitions by allowing the bots to charge while standing. Unlike earlier robotic platforms that required lying down or removing components for energy replenishment, Optimus Gen 3.5 appears capable of maintaining full structural integrity while connected to the power source. This is more than a design choice. It implies a charging system engineered for both speed and durability. Initial estimates from industry analysts suggest that each charging station may deliver power at a rate of 1.5 to 2.0 kilowatts per bot. If accurate, this means a standard Optimus unit with a battery capacity of roughly 2.3 kilowatt-hours could be fully recharged in approximately 70 to 90 minutes. However, Tesla's previous filings and Gigafactory test logs hint at the existence of advanced thermal regulation, which would allow higher throughput in shorter windows, possibly cutting charge times below the 60-minute mark under optimal cooling conditions. Speed is only part of the equation. The elegance of the charging architecture lies in its simplicity and modularity. The stations are designed like lockers or vertical pods, spaced precisely to prevent heat accumulation while maximizing density. Early observers have noted a gap of approximately 1.5 to 2 feet between each unit, which facilitates both airflow and maintenance access. This spacing suggests that a standard 1,000 square foot room could accommodate up to 60 robots simultaneously without risk of overheating. For large industrial deployments such as warehouses, gigafactories, or disaster relief units, this kind of density is a game changer. Another point of interest is the apparent contactless interface seen at each robot's midsection, aligning with the chest or abdominal area. While it's difficult to confirm from a blurry image, this design hints at Tesla potentially using inductive charging or hybrid contact solutions, minimizing wear and tear on physical ports. If true, this would drastically reduce downtime due to mechanical faults and simplify long-term maintenance. It would also suggest some level of intelligence in the docking process. Robots identifying their assigned bay, aligning themselves autonomously, and engaging the charge with near-perfect precision. Beyond the hardware, the implications for software are enormous. A unified charging infrastructure necessitates real-time fleet management software, which Tesla has experience with via its vehicle supercharging network. Applying a similar logic here, Tesla could track Optimus battery health, deployment schedules, maintenance needs, and charging priorities via a centralized AI dashboard. A robot returning from a heavy-duty task, such as lifting boxes for 4 hours, might be given higher charging priority than a bot that was performing light-duty reception tasks. This scheduling dynamic introduces not only efficiency, but longevity into the life cycle of every Optimus unit. Moreover, Tesla may be taking inspiration from energy buffering techniques used in its supercharger stations. By including stationary batteries behind the charging wall, facilities could reduce draw from the grid during peak hours. A 1 megawatt-hour power pack system, for example, could charge over 400 robots partially during off-peak times, distributing energy intelligently without overloading infrastructure. This allows facilities to deploy large numbers of bots in urban or rural environments with limited electrical capacity. But perhaps the most important aspect of this charging station isn't purely technical, it's symbolic. Tesla isn't just building robots, it's building ecosystems. Each robot is a node in a much larger operational network, and centralized charging hubs are the nervous systems of these networks. How do you maintain hundreds or thousands of robots daily without human intervention? The answer begins here, with scalable, automated, modular charging infrastructure. Some observers have speculated that this image could indicate pilot programs in logistics or military-adjacent sectors. The layout resembles military barracks or secure training facilities, and Tesla has recently increased hiring for Optimus integration specialists in high-sensitivity deployment zones. While not confirmed, the architecture shown aligns with use cases requiring tight control, high uptime, and predictable maintenance. Additionally, one must not ignore the role of environmental considerations. Charging heat is a byproduct of high-throughput systems, and Tesla's ceiling-mounted fans, visible in the image, indicate proactive climate management. Given Optimus's skin is made of silicone-based materials optimized for human skin-like compliance and thermal tolerance, Fahrenheit to 176 degrees Fahrenheit, it still requires ambient control to prevent overheating. This further emphasizes the importance of architecture. Cooling is not a separate layer but built into the spatial design. On a broader scale, if each Optimus Gen 3.5 can operate for approximately 8 to 10 hours per charge, facilities would need to cycle their robots in shifts. With 60 bots per room, a 3-shift rotation would give 180 units operating 24/7 with just one charging chamber. This reduces real estate costs, minimizes downtime, and allows for flexible scaling. We appreciate your contributions and hope you will have the most relaxing feelings after watching this video. If you did, please hit the like button and join the Techno Creator family by subscribing to our channel. And don't miss out on any of our awesome videos by hitting the bell icon. We value your feedback and your time. Thank you so much for watching, and we'll see you soon. Until then, stay safe and have fun.